That's the new one or the old one?
That's the old one.
That's the old one. So, oh yeah, that's everything there. Yeah. And it's going to be about Langevin's equation for landmarks.
Cool. Thanks, Laurent. So, yeah, really nice to be here and to talk. I'm actually part of one of the other programs here, the growth and form one, so I'm going to try and justify my crossing between the programs a little bit for the first few slides. So, the reason for the growth and form meeting has been to talk about this book by Darcy Thompson called On Growth and Form, which was published in 1917, so it's kind of the centenary anniversary. And Thompson wrote about the idea, so he had a big thick book, one theory called the theory of transformations, where he wrote about this idea of comparing related forms, or biologically related forms. And what he really wanted to say was, you can see very complicated changes in the biology, the appearance of things, but the changes themselves don't have to be complicated. Just because the forms are complicated, the changes can be something that it's easy to understand and interpret and analyse mathematically. And really, what he was trying to do, I think, through the whole of the book, was try and persuade mathematicians that they should do biology, and that there was as many things to do in biology as there had been in physics for a long time. And I really like that quote in the middle. It's not the biologist with an inkling of mathematics, but the skilled and learned mathematician. And I'm not doing the skilled and learned, but I do claim to be a mathematician, at least. So this was Thompson, and as part of this program, I spent a week in Dundee and St Andrews, where he was based, and discovered this guy was even more interesting than I'd already thought. So this is a picture of him in about 1940, when he'd taken to walking around St Andrews with a parrot on his shoulder. And he'd been given the parrot by the captain of a whaling ship, because he'd been persuading all the whalers of Dundee in particular that whenever they found interesting animals, whenever they were fishing or whatever and they found interesting animals, they should bring them to him. And he also went around most of the zoos of the UK and persuaded them that when animals died, they should also send them to him. So I found this amazing letter written to him by the zookeeper of the London Zoo, which said, "One of our giraffes died, we've put it on the train to you." So it had gone from London all the way up to Dundee for him to collect, and he then had a museum where he kept all these things and had them prepared. So let me tell you a little bit more about what he was trying to do, which was to say we should have these transformations between shapes, between species of animal, and this is kind of his most famous set of pictures of these fish. So on the top line, on the left, we have a fish where he's carefully drawn the picture of a fish. He's put a nice rectilinear grid on it, and then he has deformed the grid, copied the appearance of the fish underneath it, reasonably carefully, possibly, and he's then claiming that it looks like a new fish. Now it turns out he didn't do any of these drawings himself. Having seen a whole load of his letters now and seen his ability as an artist, it's kind of about the same level as mine. He had some students who he employed in order to do the pictures for him, and then he annotated them and labelled them later. So here we have some of the pictures that he used, and really what Thompson wanted to say was that the transformations that we use should be, or that he used, should be simple. And he keeps on using this word simple, and it's quite funny because, for example, Laurent yesterday told us that we and people doing diffeomorphic shape transformation and LDDMM have inherited Thompson's ideas, but we use an infinite dimensional group, which is probably as not simple as you can make it without a license. And everything he was talking about here is in some sense a simple transformation. We've got a shear here, and we've got a isogonal or reasonably conformal or Mobius transformation here, and then this one that my student looked at and just described as strange or peculiar. So this transformation. Now, and it's quite interesting, in the book he spends quite a lot of time apologising for using this one, but it's as simple as he could make it, and he argues that it's somehow simple, which I think is a nice phrase. He follows this by then looking at the human skull and arguing that if you take the transformation from the human to the chimpanzee and then keep on following that same path along, you end up at the baboon. So it's more of the human to the baboon is just more of the transformation of the human to the chimpanzee. So this is kind of the idea of following some path and continuing to follow the same path to get some idea of a transformation. Now there's a whole series of problems with these pictures when you start to study them a little bit. So one obvious problem here is he's claiming that he's taken the grid on the left, he's deformed the grid in this way to get the chimpanzee and deformed just the grid again to get the baboon. But somehow, the teeth have definitely changed quite impressively as well. So there's a whole load of non-local transformation going on that he's not talking about. And having done these transformations with other pictures, if you take the human and make it look like a baboon, the teeth do look pretty strange. And if you do it the other way around, you can get a really scary looking human. There are some other problems with these pictures as well, where the human skull that has a big lump like that at the back of the head would look pretty weird. If you talk to biologists about these pictures, they'll tell you all the problems that there actually are with these things. So there's kind of quite a lot of artistic license in what he's doing. And still nobody is yet convinced that there's any actual, well, biologists that I talk to are still not convinced there's any actual idea in there either. But I think it's a really nice thing to study. What he did though, and this is the follow-up for talking about diffeomorphic transformations, we do image matching, we deform the images, and well, Laurent told us a bit about the idea of between doing landmark matching and whole image matching and what we deform. These are some letters that Thompson wrote to somebody who wasn't related to him, somebody who wanted to use the idea, and he pretty much explained what he's doing. I just put this on there because he really points out this idea that what you do is you look for landmarks. You look for points that you are pretty sure correspond between the pairs of images. And you use those points. So you assign those, match those, deform the grid, and then keep on copying the thing across. So it's exactly like when you're a little kid and you want to make a bigger version of something. You take a small grid, take a bigger version of the grid, and carefully copy all the lines. It's exactly the idea of what he wanted to do. And then there's a second quote which pretty much says, I'm not doing this for real in the sense of I don't want to make one person's head look like another person's head. I want to make the idea of biology to have this simple mapping and everything else will just be noise and variation that you see from within that. All that is a long discussion to try and get to the idea of doing image registration with landmarks. So Laurent showed us lots of things where you can do image registration by just actually deforming the whole image and doing similarity matching across the whole image. For this talk, I'm going to just decide that we have some landmarks. So in other words, we have a set of points that we have defined on an image, and from those set of points, so here are some zoomed in pictures of, so these are brain images, and somebody is carefully drawn around, or semi-carefully drawn around, and put some points onto the ventricles, so the holes in your head. And here are those points that have been labelled on a set of these brain images. And what we want to do is find some transformation of those points so that we transform the points on one image to the points on a second image, and then we'll use some further mapping function to take the whole of the image and transform the rest of the image according to the idea that those points match. So there's a whole set of assumptions inside here, one of which is that we have these points in some sense of correspondence. So that these points have been nicely labelled, have been put down by somebody who knows what they are, and that we have exact corresponding matching points on each pair of images. And the whole point of this talk is to try and look what you can do if that isn't quite correct. So normally when we think about how to do this flow, we've just got a set of points in R2 on each image. What we want to do is find a mapping between them, and normally we restrict this mapping to insist it's a diffeomorphism, i.e. it's invertible and both it and the inverse are smooth. And then from that we can define a velocity field which tells us how to move the points, that will tell us if we imagine the landmarks being on image 1 at time 0, they will end up at image 2 on the same matching points in image 2 at time 1, and then we can just construct a velocity field that tells us how to move those, and we can project that out to the whole of the space, the whole of the image space. So various ways to do that. The way that I've been doing this for too long to think about now is to expand it out to say the velocity field is constructed as, if we take a set of points Q, we can define those points as being everywhere on the image. We have some landmark points, which are these QJs. We just need some Green's function, and we need to get, because this is a velocity field, we define each point as having an initial momentum, which is going to start moving along, and then we just solve the flow. So all we're doing is solving this equation for some choice of Green's function for the parameters we've given it, which is some set of initial momenta p and the points that we've defined as landmarks, which are the Q's. And if you do this, you get a fairly simple optimization problem. So what you've got to do is minimize between time 0 and 1. So remember, we've got the idea that the landmarks start at time 0 on image 1, end at time 1 on the second image. We're going to just minimize this optimization problem, and the constraints that we have are that the velocities match and that the initial and final points of the landmarks are the position on the first image and the position on the second image. So this just gives a normal constrained optimization. We can calculate derivatives and we can do gradient descent on here. And the only thing that I've obfuscated really is what this g is. And it's called g because it's a Green's function and there's many choices. Laurent slipped past one picture of doing this with the idea of landmarks and how they might move. What I'm going to show you is just assuming that this Green's function looks pretty much like a Gaussian. Now that's in some sense an odd choice, and because it's a non-Comet supported function, so the thing will continue, the image will continue to be formed all the way to infinity, but it's easy to define. Because I'm just doing landmarks, this is a finite dimensional registration. I've just got a set of two-dimensional points for as many landmarks as I've chosen to put on my images. So having defined this, you've got a really natural setting in which to do optimization. You can just run this thing forward, and now what you can optimize over are the initial momenta that you give. So it's just a shooting problem. Pick some momenta for your landmarks, flow them, see whether you get a good match at time 1. Calculate derivatives, go back and improve. So it's just literally a shooting. Run the whole thing forward, change your momenta, do again and again. And this will give you as good a match of your pair of images as you can get to in the time you allow, or at least into some local minimum. And the way we do this is to transform it into a Hamiltonian framework. So it's just solving the boundary value problem for this Hamiltonian ansatz, particle ansatz, to just say we got position and momentum of these particles, we've got a function, and then we've just got these boundary conditions. So everything we do just says we need to integrate everything forward in time. So choose your favorite integrator, and we need some momenta, which is the thing that we can then do some optimization over. And everything else just consists of saying, well, now let the thing flow and go and do the optimization. So we can do that, and we have been doing that. I guess I've been doing that since 2005, using literally this method. There are two real parts to the uncertainty that I want to think about, though, and this is back to that idea of Thompson's of landmarks and how do they correspond, and back to this question of, well, how do you put those landmarks down in the image anyway? And there's really two places where this uncertainty comes from. So one of them is somebody has to put those landmarks there. You can get a computer to put the landmarks down, and it will make some estimates according to your choice of algorithm about where the edges are, where the corners are, whatever else it is that you're defining your landmarks on. Or alternatively, a human has to come on and click on the points that they think are in correspondence between the images. Either way around, there's some uncertainty and some error in the way that that works. And then also the velocity field that's a long way from the landmarks, kind of in that Green's function, we've got this inherent assumption of what's going to happen there and how the image will deform at those points. Ideally, we'd probably like to say if we don't know anything, it shouldn't move at all. But it's a piece of uncertainty we've built into this at the moment. So what we'd like to do, the purpose of doing this talk at all, is to incorporate those ideas of uncertainty into this kind of framework. Let me just show you that this kind of matters. So this is a traditional shape model of those ventricles. So I've literally just taken those points that somebody had defined by drawing around the ventricles, clicking on points, picked up those positions, and just done principal components analysis on the positions of those points. And now I've defined a shape model that says, well, what kind of variation can you expect to see in sets of real human ventricles if you look at doing this in a linear space? So this is the kind of motion that you get. So this is either a really, really bad model or really bad points. Oops. Let me not show you my other picture yet. Okay. I guess we'll go back. So it's either a really bad model or a really bad set of points because, and it's actually visible inside here. So somebody came along, and actually these points were all put there by medical students. This was somebody given a whole set of images and asked to actually come along and put down where the points were. And they're not doing it particularly well. So here, they got some of the points backwards. The ventricle gets quite narrow and quite thin, and they ended up with some of the points that were meant to be on the left on the right of the ones that should have been on the left. So the ventricle kind of folded itself over, which isn't very good for you. In fact, if that happened, your brain would probably pop out your ears and you'd die. Then we have some other points here where the two entire ventricles have intersected with each other. So it's like you've only got one ventricle instead of two. Again, this is not very good for you. So these are crappy ideas of somebody doing the labeling. This is really why we need to do this stuff, is getting graduate students or medical students or whoever to actually do this. Well, it's probably better than asking me to do it, but it's still not a very good way of getting accurate points. And the assumption of the shape model is that all these points are in correspondence across the whole set of these things, and the chance of that being true is really not large. So what did we do? We weren't the first people to really think about doing this. FX, who is here somewhere, with Alain Trivet, had thought a bit about this previous to us, but we had a different formulation of the way this is done, and this has been followed since by Daryl Home and Stefan Sommer have thought about kind of related issues as well. But let me just tell you about our version. Daryl can maybe say a bit more about what he did tomorrow. So what we just thought was, the way we have actually formulated this entire problem is based on the Hamiltonian. The Hamiltonian is a first integral of the motion, i.e. it's conserved. So we have something that is explicitly conserved, the energy, the Hamiltonian of this thing, and therefore if we imagine enclosing the whole system into a heat path, then what we can allow is that in equilibrium we should have this thing sitting at a constant temperature, so we still have a conservation law. And this just leads to the Langevin equation. So you imagine taking the system, particles moving, something with energy, and you're allowing the excess energy to decay into the heat bath, so that in equilibrium you still get constant temperature. And the way you do this is to introduce some stochastics. So given the potential energy, which we've called V here, your stochastics change. The update for the Q equations is still exactly the same as it was before. So we had these equations here. The Q equation has stayed exactly the same. The P equation now has two forms. So one of them is we've added in a noise term. So this is just a Wiener process that with parameter sigma that we've added in. We integrate this up in order to get a Brownian motion term. And then we have a coupling term here where we have a lambda. So the P, the momentum term, now includes a bit of itself in terms of its update. So that's the only extra thing that we've changed. So we end up with a Brownian motion term coming from a Wiener process and this coupling term that comes up when we allow for the fact that this bath is taking away the excess energy, so we get a coupling that arrives. Now, because this is a Langevin equation, because of the way we've set this up, this has the Gibbs distribution, this distribution here, as an invariant measure. So in equilibrium, we've got something where this still has a probability measure defined, and this Gibbs distribution is just a function of the Hamiltonian. The Hamiltonian now is split into two terms. One of them is the kinetic energy, which we had before, and the second is this potential energy that we've added in, so the amount of energy there is in the system in equilibrium. And the only extra thing we have is a term which balances out how much of the P we've included against how much of this Wiener process, the Brownian motion, we have. So it's something that is called inverse temperature in the literature, but it's just a ratio of how much of these two terms you're allowing. So with the version we're using now, so this was the classic system that we end up with. We can write this system down in the same formulation as we had before, and it looks pretty much exactly the same, except for we've explicitly written the Hamiltonian in now instead of the P and Qs. The Gibbs distribution is still invariant, so we still have an invariant measure, and it's still in fact the Gibbs distribution. And what that means is that if we have very high temperature, then the system gets concentrated at very small energy levels, and if we've got a low temperature, then everything is smoothed out everywhere. So it gives you a kind of control parameter that you can allow to see what's happening. So having written this down, you can then just go ahead and use reasonably standard methods to find solutions to this problem. So what we're going to do is say, well, we know where the landmarks are. Somebody gave us those, but we're going to assume that the person who gave us those was drunk, so they've made mistakes. Now, we've got landmarks on the first image, we've got landmarks on the second image, but again, they were done by the same idiot. We've got the same kind of idea of noise in both of them, and we're going to treat those noise as independent and identically distributed because there's no way we can include correlations between them. So we're going to assume that on average those landmarks are correct, they're zero mean, but they are IID. And this kind of system was studied by Martin Hira, Ian Stewart and Voss in 2011 under the assumption that this Hamiltonian could be split. So when I said the Hamiltonian could be split, I mean that we can actually explicitly write it down in this form of a potential energy and the kinetic energy separately. So in that case, there are some nice known results for doing this in finite dimensional cases. Let me just show you a bit about what I said about the inverse temperature. So if this inverse temperature is high, then if we allow a perturbation from, so this is what I've given you, is the circle is my initial solution. Then I've said now we've got landmarks, that are noisy, so show me a possible solution that you might get around it. And it's fairly close to what it should be because the noise temperature, this temperature thing is high. As we let the temperature get high, which means the inverse temperature gets smaller, then we get things that are far further away, get more variation allowed, so the position of the landmarks can change a lot more. So we're just allowing more noise and more uncertainty in the system as we do that, and you can see the effect of it on the grid in the dots. So allowing this temperature to change really allows kind of how wrong you can imagine the person might be. So it's giving you something that says what you're allowing in terms, and you can fit that from your data if you have enough data. So how do we go about solving this? I said that Hira and co had done this. So what you do is you define this thing called a Brownian bridge. So Brownian bridge is something where we say, well, we've got some initial time point 0, that's where our landmarks are to start with. We've got some final time point 1, that's where our landmarks end up. A Brownian bridge says we want the distribution to be conditioned by where it actually ends up. So we want to know that we end up at the right place. So this, at time, I called it W capital T there, but capital T is 1 in this picture. So it's something that says we start from some position, B equals 0 here. We do a random walk by just allowing the thing to vary. Here's the position on a one-dimensional random walk. And we want to always end up, so we end up in the right point. So what we're going to say is this is all the random walks where if you start from time t is 0 at 0, you end up at time t equals 1, you end up with the same position. You end up at 0 again. So it's any random walk where you go wherever you feel like, but you end up in the end back where you started. So that's a Brownian bridge, and you tend to assume there's no noise on the boundary conditions. So it's exactly the opposite of what I really want. I want to say there is noise on the boundary conditions. The boundary conditions are my landmarks, but here's how you actually do this. And then so here is a Brownian bridge condition on that idea that we get to the endpoint at the time is 0 thing. Now, the reason why this can help to do what we want is this idea of Brownian motion says, well, Brownian motion itself is just random perturbation. It's just a Gaussian random field, and if it's a Gaussian random field, it's defined by a mean and a covariance. There's nothing else left to find. So we can condition that Gaussian random field on what we see. We can condition that Gaussian random field on sets of landmark points. So we then have something where we say, well, here are the points that we actually saw. These are the ones that somebody gave us for this image. Here are the ones we saw for the second one. And this gives us a second Gaussian random field. It's not the first one because the first one was independent. We've now conditioned it on these points. But the update equations for that are very well known. They were written down, I don't know, nearly 100 years ago. And what's important about it is the covariance doesn't actually depend on that position that we end up with, so the final condition point. So the covariance doesn't depend on that. That's kind of carried over into the mean. So everything else is perfectly well defined and reasonably easy to solve. Now, the next trick, and the one that's been around for rather less time, so this is really what Hira and co came up with, was if we've got this idea of doing solutions through this Brownian bridge, can we extend it a bit further? So we want to estimate parameters of our set of differential equations. So these, for me, the parameters are the amount of noise I should allow, and that's coupled into this temperature. So really the parameter I'm interested in is this idea of temperature. And what you do is you extend the idea of a Brownian bridge into something called a diffusion bridge. So the diffusion bridge just says, well, it's not just enough to just allow completely a random walk, we've got to allow the kind of the noise in the area to diffuse and move out from there. So this process here is a diffusion process. It's got the same kind of thing going on here, some Wiener process, at least when we integrate it as a Brownian motion, but now this is actually a parameter. So that sigma has got a parameter x, so it's got an actual coupling inside. So we've got some function of our process with respect to time, and then we've got a coupling thing, so the covariance is now including the information about where we are in the process. So this changes the bridge. It changes the bridge to give you a slightly different version of the stochastic differential equation, and the only thing that changes is we get this log likelihood looking estimate for what's going on. So it just changes that instead of what we're estimating, just changes a little bit. And this thing here is called the Doob transform, presumably named after the guy who wrote it down. Doob himself called it the H transform, but everyone else seems to call it the Doob transform. The problem with doing this is it's really hard. What we've got here is the derivative of the log of the probability distribution. And it's really hard to find what that probability distribution looks like. So the transition density is called here. So it's really hard to find what that looks like. If you can find that, everything else is reasonably simple. And the reason why it would be good to have is all it does is change the measure. So we had this invariant measure, the Gibbs transform. By applying this transformation, all we do is we change that transformation, and we do it in a nice, well-defined way, this thing called the Gersanov formula. So that just tells you how the density changes. And what it gives you really is something where you can do rejection sampling. So rejection sampling is a way of sampling where so it's just a way of forming a Markov chain Monte Carlo system where you sample, and every time you sample you make a choice about whether or not to keep that one because it looks like it is from your distribution, or throw it away. So we can sample from the original process and use this transformation to decide whether it would still be a useful one to keep from our current process, and keep on doing that. So the only extra computational cost we would have if we knew what the P was calculating that Doob transform. Unfortunately, in general, you don't know what that P is. So what you do is you keep on doing simulations. This is kind of like actually the way I think of deep learning, which is if a bit of randomness is good for you, more randomness must be better. So here we use more randomness and more computer time in order to do more estimation, and we keep on throwing away the things that don't fit into our distribution that we expect to see. So what we do is we start from time t equals 0 and we do our random walks, and we start from time t equals 1 and we do our random walks, and the paths that will work are the ones that meet somewhere in the middle. So we keep on sampling, and the ones that meet are the paths that we actually want. Those are diffused in both directions and come out with the right place. So it's a perfectly good approximation where we're just throwing away any paths that don't meet in the middle. And the problem with doing that is even in one dimension, the number of paths that meet in the middle isn't that high. And in fact, as you start doing this in higher and higher dimensions, the number of paths that meet tends to have measure 0, which is not really a good thing. So there are two things you can do at this point. One of them is you can try and find a coupling method that tells you how to find the forward motions and the backward motions so they meet in the middle. And sometimes you can do that. So there's a series of papers, Delion and Hu, was one particular example, where they thought about the idea of saying, well, could you make it so that your forward process and your backward process, you could add the drift term so they get more and more likely to meet in the middle. So in other words, this path's doing random stuff, this path's doing random stuff, and then you start to guide them to point at each other. And it turns out you can do that. It destroys all the mathematical proofs you have of the thing converging, unless you're very, very careful in how you pick the things. But numerically, it works really well. So Stefan Sommer has done quite a lot of work doing that, and that's exactly what it is. If you see these points and you see them drifting, and what they start to do is, initially they're doing genuine Brownian motion, and then they start to really move towards each other. And if they're a very long way off when he starts to apply this, they move really, really quickly towards each other. So it does screw up the whole idea of having an invariant measure and all the things around it. But numerically, it works beautifully. So, yeah. The other place where I know you can do this is you can follow Martin Heirer's methods. So you can argue that if the Hamiltonian is separable, i.e. you can split this thing into a kinetic term and a potential term with no interaction, you just replace the Hamiltonian by only looking at the potential term, sorry, only looking at the kinetic energy term and assuming that the potential gets covered by the drift. And that linearizes your SDE, and that's great. Unfortunately, we don't have a separable Hamiltonian, so this method isn't going to work, and we're definitely working in reasonably high dimensions. I mean, how many landmarks do you need to define for an image? 50, 100 more? So we're in at least 200 dimensions or so. So we've got a real dimensionality problem, and the clever methods of doing it, certainly the theoretically principled clever methods of doing it, actually don't work for the way that we think about doing this. So last year or the year before, when I was working with Tony and we were talking about this, we went up, and I gave a variation on this talk up to this point in Warwick, because I was really hoping that Martin Heyer was going to tell us that this was a great thing to do, and yeah, it wasn't. he sort of said, good luck. So what we did was to cheat. If in doubt, if you got to the stage where you're pretty sure that this isn't going to work properly, then do the mathematically most naive you can think about, which is do some approximation. And if you're going to approximate, you might as well do it properly. So what we realized was the trajectories for the Langevin equations should originally be reasonably close to the Hamiltonian solution. And we know we can construct the Hamiltonian solution, it's the one with no noise. So all we're going to do is construct the normal Hamiltonian, and then I'm going to linearize about the center point. That's the point that we'd like the forward diffusion and the backward diffusion to meet at. So we're going to linearize about that point, and then allow the thing to integrate forward and backward in time from there. So write everything down linearly and simply. So pick the Hamiltonian solution, so literally assume these landmarks aren't noisy at the start and the end, calculate the flow that you would get from those, pick the center point, so time is a half, linearize about that solution, and then propagate forward and backward by assuming that this thing is Gaussian, because you're linearizing, you might as well keep on making simplifications that make your life as easy as possible. So all that means is we have to apply the same Gaussian process update equations as everyone else uses to calculate what the mean and covariance look like as we move this process forward and backward from that point. And to do that, well, it's actually surprisingly easy. You can just, because you've linearized it, really simple numerical methods work, and you condition based on the noisy versions of your distribution at both ends, so on the landmarks that you've got at both ends, and as many sets of those as you've got. So all the work now consists of do the same thing we've been doing for 12 years anyway, then linearize about that point and solve it forwards and backwards, and then do some conditioning on the distribution that you see over the data from those points. So here's some pictures of what you get. So here is a registration that's meant to be a registration of a circle going from radius 1 to radius 2. So look on the top left, you see a noisy version of the circle of radius 1 and a noisy version of the circle of radius 2 in orange and green. And those solutions, what you can see, hopefully see, is the paths that those landmarks take to move from those. And you can see that those paths are nice and smooth. So although we've got a noisy version of the problem, because the landmarks are noisy, the paths that all the landmarks move along are now smooth in the space. What you can see here are the uncertainty, the covariance, plots of the covariance, so the uncertainty in the positions of the landmarks on the original image and on the second image. So this is just a backward plot of what the covariance structure looks like, and you can see it's kind of centered around the right points, and the points that are closer to the original circle have got less covariance than the ones that are further away. So this doesn't know anything about meant to be in circles, it's just got data, it's trying to find some matches, and the only thing I really want to point out on here for now is because we've linearized and because we're not adding noise to the motion, we're just adding noise to the positions, the paths that things follow are smooth and well behaved. So this is different to the other way that people now do this, where they add noise onto the momentum, and what you see then is you see the paths are really jaggedy. So that what they say is, let's assume the landmarks are good, but we make errors as we do the integration, and then we get a different noise term and we end up with very different paths. So again, if you look at Stefan Sommer and Darrell Holmes' work, that's what you'll see. They've added noise into the momentum, not into the position. Okay, so then we did that, we thought about it a bit, and then suddenly we realized that actually, instead of doing an approximation by just linearizing around the center point, we do something a little bit different. we can do an operator splitting. So we can just actually take the generator of our motion and write it down in terms of two terms, one of which is called the Liouville operator, and another of which has got this second term here. Both of them end up, one of them is a second derivative term, one's first derivative. They're both Gibbs invariants, so they both still have that same Gibbs invariant measure that we had before, and they also have a Baker-Campbell-Hausdorff formula, i.e. we can actually go and do some estimates of these things. Now this splitting is called a Strang splitting, and it's a kind of standard thing that people do in the literature on this, and there's lots of Strang splittings. This is just the one that's nicest, simplest, and easiest to look at and think about. So when we did this, I wrote down, Tony and I had a kind of conversation about what we might do. I wrote down one splitting, which was the top one, and he wrote down the second splitting, which was the second one. So what they are is the top one says, do half a step in, so remember the difference between these two is just the two bits. We've got the generator split into two parts, one of which has this sigma squared term. So I figured we could do a step in the one with the error, with the covariance, a half step in that one, a full step in the one that is the full generator, and then a half step back in the first one. So it's splitting it up into two terms. You do a half time step in one, a full time step, and then a second half time step in the first piece. And Tony, who knows far more about stochastics than me, did it the other way around. So suddenly the interesting question becomes, well, what's the difference between them? The reason why people do this one is you can then construct averages. So you can actually do computations based on this. Because of the splitting, you can actually go and look at the set of positions you have which parameterize everything, and you can construct averages. And the Gibbs distribution sits over the midpoint, which was this point that we linearized out in the previous time. The one for what I did, it turns out you can construct the map estimate, so the maximum posterior estimate, so the thing that you would use in machine learning and statistics if you wanted to look at how these things looked, and you can do that by using a Laplace approximation. So the top one is, they've both got a Hamiltonian flow. They've both got this flow of, we know that the energy is conserved because it's a Langevin equation, it's sitting inside the heat bath. We know everything moves and flows downhill. All we've got really as a difference is how we actually construct the thing, and then the difference is whether we look at the posterior and say, well, we can't actually compute it, but here's the most likely thing that you would get from it, so in the top case. And in the second case, it's actually fully parameterized, and we can literally construct averages, so we can look at center points in the space. When we tried to interpret what they meant, we realized they led to different semigroups, and then it turned out that actually calculating the time half steps was a lot harder than I thought it was going to be, certainly. So actually doing that step and making it work correctly so the thing actually converges turned out to take nearly as long as thinking about them and doing the analysis. Hey, that's computers for you. So let me tell you briefly about the Laplace approximation. So remember, we want to get to the idea of having the map point, the most likely point of this distribution under that splitting. So all we need to do is to realize that this is just an optimization. We're just trying to find the most likely point. So we evaluate that by writing down a Gauss-Newton iteration that will lead to that point, and that enables us to construct averages. So if you give me lots of sets of landmark points, so literally just like I had for those ventricles, lots of people labeling them all the same, now we can actually go and construct what this thing would look like by writing down the average here across all the flows between each of these pairs of points. So all you have to do is go and construct how you would flow from the first person's landmarks to the second person's to the third person to the fourth, and so on in between. And then, given that, you can actually construct the average across the whole set. So here it is. Here are two samples, two noisy estimates of some shapes. It's really unclear what's going on there, so let's just think of this as a tangly mess. Theoretically, it's the same shape twice with lots of noise. Here are the two shapes registered, so you've got the two of them put together. You can hopefully see on there it's done a pretty good job of lining them up and saying they are the same. And then what we've got around each of these things is a covariance of how certain it is about how good that landmark is as an estimate. And this is only based on two things. As we increase the noise parameter, so the temperature, then it gets progressively more uncertain, but the registration is still really pretty good. There's a few places here where it doesn't match, but it does a reasonable job. If we start to increase the number of samples, so here's 16 samples from it, so again a really nice tangly mess of noise, but the registration's improving and the estimates it's making of the covariance structure, the error it's allowed to make around each of these is getting tighter and tighter. And as you increase the number of points, again, it continues to get better and better at doing this. So we can start to use, if we've got enough data, lots and lots of samples of the same thing, with really quite large amounts of noise, we can make really quite good estimates of this thing and find good registrations between them so that we get individual points, and the average corresponds pretty much to that place. So, having got here, that's the end of the main part of the talk. I just wanted to add in a couple of things, which is to think about how much further we can actually take this method. So, what I've written up is the full version of if you allowed for all the variation you would allow within these stochastics. So what we've got is noise in both Q and P added in. So again, we've got this Brownian, or the Wiener process, which is going to integrate to give Brownian motion, and it's been added into both the Q and the P. Now I've given them the same amount of noise. The sigma is the same in both of them, and that matters because that's the only case in which we can do the analysis and see that we get an invariant measure coming out. Effectively, really what you're saying is that the noise in the two processes can cancel out in some sense. So that's relatively important. From there, I've allowed the coupling, so I've got now two parameters, lambda and mu, which are just telling me how much of how much the positions are affecting themselves, how much the momentum are affecting themselves. So we've got two different pieces of what's going on, and we can also add in that drift term which biases things to say you should move towards the correct place. And then we can go and look, given this is a Hamiltonian, given we know this is on the diffeomorphism group, we can start to go and look for the geometric structure that we have. So particularly, there are conservation laws that we know. This is a Hamiltonian, we know energy is conserved, and under this Langevin version, energy is explicitly conserved. There are other first integrals of the motion that we can exploit, and in fact there are Casimirs that we know are also conserved, so these are just products of Lie brackets that we can see are preserved in this. So there are whole sets of geometric things we can add in the hope of getting a bit further. As an alternative idea, perhaps we can start to think about where else we might want to add noise. So given we can think of these as flows on diffeomorphisms, given we can think of the metric as encoding the information, can we add noise and error into that metric or make that metric spatially varying in order to actually go and do some learning and to fit that correctly? And another thing that you might want to think about in the same way is, are there preferential directions? If we think about how people make errors, maybe we can see that people make systematic errors in particular ways, and we can start to go and include some structure from there. So those are all places where this kind of methodology can hopefully help to make some estimates. The other thing I wanted to show you is this. So this is very recent work with Klaus Modin, and in fact based on the previous meeting we had here 3-4 weeks ago. So what we're thinking about is, say you have a random walk on S2. So you just have a random walk that you find on the surface of a sphere. So you just think about points and doing a random walk, Brownian motion around there. So that's two-dimensional. Now if you lift that up to the whole motion you might allow on SO3, so the Lie group SO3, what you would hope to see when you do that lifting, you've got horizontal, sorry, maybe I should have thought about how much maths you told them yesterday. So you've got whole motion there. What you would expect to see was still, your noise should be kind of in 2 dimensions. And the diffusion will start to show you the diffusion spreading, so you'll start to see the position of all the estimates of the points moving out in 3 dimensions. So what you can see here on the left is you can see little points, 3 points, which are just the coupled vectors x, y, z, based on the idea of doing some random walks on S2, so in 2 dimensions, lifted up into the 3-dimensional group. On this side, you're going to see the noise just doing the estimates on SO3. So what you should see here is noise in all 3 positions will all kind of spread out and diffuse all at the same point. Here, there should only be noise initially, at least in 2 dimensions, because we're only allowing the thing to walk around on S2. So that's here. You can see, so the blue is the points that we're actually thinking about. The blue is the points which are moving around. So you can see they are nicely sitting on the surface of the sphere. But you can see that the same amount of noise appears. You know, we're doing motion in the z direction, then everything's around there. We get the same amount of noise coming in the other directions. Over on this side, where we're lifting the random walk from S2, you can hopefully see that we're actually getting one direction pretty much is where the noise is appearing. So although we've got the whole thing varying in exactly the same way on the top, this coupling has given us tighter ways of holding these things together. Unfortunately, over time, this thing does diffuse out. And what you can see is that diffusion is starting to spread as we keep on integrating. But now this one is pretty much covering the whole of the sphere, and this one is still a lot tighter. So there's no numerical things going on, it's just the fact that the process is diffusing out across the whole thing because of that coupling through time. So let me tell you what we've done. We've introduced a way of adding noise into the landmarks by saying, well, the noise is something where we can think about, we've got energy conserved, so in order to conserve energy fully, we embed the thing into a heat bath, giving the place somewhere to go, and we think about the equilibrium distribution once everything's settled. So that gives us a Langevin equation, which is then just a prior distribution over the set of deformations that we allow. Once you do that and you start to follow it through, you discover that the bridge that you'd like to sample from is computationally problematic. So you can either linearize around a point, or you can do this operator splitting, and they give you kind of, in some sense, complementary methods of doing this stuff. One of the splittings that we considered enabled you to define an average. The other one enabled us to define a maximum and posterior estimate of where the things were. And what I showed you was the samples that if you have enough data, you get good estimates of where those points should be. And then I started to ask some questions of where you can go from this and how you include some geometry and where that might lead in the future. So, thank you very much.
Are there any questions?
So for the last simulation you showed, can you just summarize what is the main message?
Good question so far.
So do I need to understand the following? So you are looking at diffusion on a homogeneous space,
Yep.
the sphere. You're looking at the group upstairs.
So you're looking at the, yeah.
And you look at the relation, the link between the two diffusions.
Precisely. So I'll write down the equations for you later, it might be.
And so what's the conclusion here?
The conclusion is, initially it does a pretty good job, but then you do get this diffusion out into the full space, so there's something going on, and actually you can see it coming out once you write the equations down as well. You can see that you get this full diffusion into the full process over time. So this is not as nice a solution as we'd like it to be.
Is it related to some mathematical properties like leaf bracketing, generating?
I think it is, and you can start to see that as we write the equations down. I can show you later.
When you drew the point correspondences, I couldn't help feeling that curve correspondences would somehow be more natural.
Yeah, so eventually the whole idea of doing this would be really nice to say that we do this on the full space of curves. Unfortunately, doing it here on a finite dimensional thing is problematic. Trying to work out how to do it over the infinite dimensional set and what that would mean, yeah, it would be very nice. I have a couple of ideas of how it's not going to work, and very few of how it is.
I've got some of how it is.
Cool. Let's talk afterwards.
Yeah.
A small question about the landmarks. So another source of error or kind of a missing information is that in addition to sort of problems in the position, you can also just have missing landmarks.
Yep.
Do you think it might be possible to have a probabilistic framework where you turn off and on certain landmarks?
Yes, it is possible to build that kind of thing into here by allowing... What you really do is a sort of cheat, because you average where they would be according to the others, and then optimize that. But yes, you can build that in, and it's... So it's not dissimilar to the way you do that in a Gaussian process framework.
What is the what is the motivation for energy reservation to start with Hamiltonian system from the beginning?
So it's a Hamiltonian system, so the energy is conserved. That's
What is the idea behind that? Why is energy reserved related to the education?
So we're doing a particle solution to finding a mapping under the assumption of a diffeomorphism. If you write down what that formulation looks like, you say that those are particles, and then the only natural thing I can think to do is to write down that particle ansatz and say, now this defines a Hamiltonian. There are other formulations you can use in order to construct flows, certainly, but this is one with a good long history of people using it in mechanics.
One way to deal it, usually people start like Brownian motion. You apply Fokker Planck, you get the diffusion equation.
Yep.
Then you are dealing with deterministic equation. Can you do something like that?
Yeah, that's actually what this is based on, is the Fokker-Planck equations there. That's the point of having the invariant measure and everything with it, yeah. I just thought I had enough pages full of maths already without adding more.
Thank you.